Okay, so here is the solution to today's hard problem of the day, which is about the function sine of 1 over x. Part A says, prove that the limit as x goes to 0 of sine 1 over x equals 0 is false, so the limit is not equal to 0. And part B says, prove the limit is equals to L is false, that is false for every value of A. So the second thing really says the limit sine 1 over x does not exist. What does it mean for it to does not exist? It means it's never equal to anything, no matter what value you look at. And the way I was expecting you guys to approach this is to look at the limit explorer. So here I have put in the function sine of 1 over x. I have a equals 0, and I have L equals 0 for part A. And if we take a value of epsilon here, so what about epsilon equals 1.22? Are there values of delta so that the entire function lives in the green zone within epsilon of L equals 0? And yeah, it looks like that works. So epsilon equals 1.22, that's fine. The entire function lives in the green zone. But of course, it needs to work for every value of epsilon. So what about epsilon equals 1.05? Oh, that still works. The whole function still lives in the green zone. There's lots of values of delta that work. That's totally fine. Okay, but what about epsilon equals 0.5? When epsilon equals 0.5, something is going wrong, and the function does not live in the green zone. And even if I make delta really, really small, so let's make delta even smaller, 0.01. So even if delta is really, really tiny, which is normally will help you out, no matter how small I make it, you sort of see you have all these like oscillations, and the sine function is blowing up. It's going to 1, it's going to -1. So it's escaping the green zone from -0.5 to 0 plus 0.5. And no matter how small you make delta, it still escapes that zone. So this is fundamentally the reason why the limit is not going to be 0. And it has to do, we found this example of epsilon equals 0.5 that will never work. There are many such epsilons. I'm going to do the whole problem with epsilon equals 0.5. Maybe you found a different value. So really the fundamental idea, let me write down the idea. A, so from the Desmos Explorer, the idea is when epsilon equals 0.5, or that's also known as a half, no value of delta works. That's the fundamental idea. And we're going to convert this into math. So when epsilon equals 0.5, no value of delta works. What does that mean? When epsilon equals 1/2, no value of delta will satisfy x minus 0 less than delta implies sine of 1 over x minus 0 less than epsilon, and epsilon is 1/2. So there are going to be values of x within delta of 0, but that are not within epsilon of L equals 0. So that's fundamentally what we have to do. And I'm going to focus on these points where the value of the function is 1. So to prove this, to convert this into math, I'm going to focus on the points where sine of 1 over x equals 1. So those are the x values where the value of the function is exactly equal 1. And you can see there's infinitely many of them. And no matter how small I make delta, there's still infinitely many of them. Okay, so what are these values? Sine of 1 over x equals 1. That means 1 over x is equal to 2 pi n plus pi by 2 for some n, some integer n. That was something from chapter 1, which means that x equals 1 over 2 pi n plus pi over 2 for some integer n. And these have the property, let's call this xn. So let xn be this thing. Let xn be this thing. And sine of 1 over xn is always equal to 1. So these are the values where the function touches 1. Okay, how does this help us? I think these points are going to show us that this will never be satisfied. So here we go. Here's the proof. When epsilon equals 1/2, no value of delta works for, what is the statement? X minus 0 less than delta implies sine of 1 over x minus 0 is less than epsilon is a half, because no matter how small delta is, so no matter how small delta is, find an xn such that xn minus 0 is less than delta. So no matter how small of a delta somebody gives you, and we can see this on the Explorer, no matter how small of a delta somebody gives you, there's always some of the xn's over here. So even with delta equals 0.005, there are values of xn in this region where the value of the function is equal to 1. So this happens, finding this xn, that's equivalent to saying that 1 over 2 pi n plus pi over 2 is less than delta, or that's equivalent to saying n is greater than, what is it going to be, 1 over delta minus pi over 2 divided by 2 pi. So as long as you find an integer which is bigger than this number, and the integers go on forever, so we can always do this, then xn is within the region you were talking about. So no matter how small delta is, we can always find one of these xn's in the region within delta of 0. And for that value, so for that value of xn, sine of 1 over xn equals 1. And if sine of 1 over xn equals 1, then what about this? 1 over the absolute value of sine of xn minus 0 is equal to the absolute value of 1 minus 0, which is 1, which is bigger than epsilon, which is a half. So what I did is I took this thing, when epsilon equals a half, no values of delta work, and it's because of these infinitely many points xn, and no matter how small of a delta you pick, I can always find an xn in your zone, and at that zone, sine of 1 over xn equals 1, which is bigger than epsilon, which is a half. So therefore, the limit as x goes to 0 of sine of 1 over x is not equal to 0. Okay, so that is the argument. It's a little bit, it's kind of abstract, right? So epsilon equals a half is concrete, but then I have to show something happens no matter how small delta is, and that was what I used these funny xn's up here to prove that happened. Okay, so yeah, that was a hard problem. I think that's a very hard problem, especially for your first day of seeing epsilon delta. So yeah, I think you should go over it. If you understand the idea, there's really two different problems. So one problem is what is going on in the epsilon delta explorer. What is this idea of this function? So if you can get that, that's a really good first step. And then the second part, which I think is really hard, is converting it into this precise math, which I did over here. I think this is more difficult. So part 1, understand the idea, and part 2, convert it into math in this precise way using the xn's. Okay, I'm going to stop there. Part B, I think, is even harder. I'm going to leave part B as a bonus. Maybe I'll open this up and give some bonus marks if somebody can write up part B. Yeah, if you're interested, actually this is good. If you're interested in doing part B, send me an email and I'll give you some bonus marks for doing part B. I think it's a tricky one.